Good morning, ladies and gentlemen, my lovely students. It's so great that you can join me here on this Thursday morning. Hope you're doing well. Hope this video finds you quite well and happy and healthy to you and your family. All right. Nice job yesterday. Heck, not just yesterday. Nice job this whole week as we talked about angles, and then specifically yesterday, triangles, right? The ones with three angles in them, hence the word tri. And we talked about a very important concept that, we all admitted pretty much at the end of class that we kind of knew that all three angles added together of any triangle should equal exactly 180 degrees. But then we also said, I didn't really know they had a name. As most things, heck, all things in mathematics do, they have a name. That one's called the triangle sum theorem. And we used it to our advantage to solve for x and find out unknown angle measures and whatnot, and did a good job. Saw your ALEKS results just a few moments ago. Whew, impressive. Most impressive. You guys are quite good at this. Now, let's take it one step further. We're not going to talk and focus so much on the angles today. We're going to focus on the sides. Yeah, because there's rules to the sides of a triangle, too. Just like there's rules to the angles that we talked about yesterday, there's rules to the sides of a triangle as well. And we can determine those rules based on something called the triangle inequality theorem. Yes, inequality. You might recall an inequality is either less than, greater than, less than or equal to, or greater than or equal to. Yes, yes, yes. And we are going to use just one of those inequalities today in the triangle inequality theorem. One of these four. Which one will it be? Well, let's find out. Now remember, as you're reviewing, you've got your textbook, your virtual nerd links, your IXL, and your Khan Academy links, all there ready to go for you. All right, let's do just a quick kind of recap of what we did talk about yesterday. We talked about classifying triangles. The same way we classify angles, we can classify triangles. And there were 6 different types. There's equilateral, isosceles, scalene, right, obtuse, and acute. And yesterday we also talked about the fact that you gotta kind of give the first and a last name. In other words, you classify a triangle, nay, you must classify a triangle by not only its angles, but also its sides together. So you have to make combinations. So in other words, this one was an obtuse scalene. Remember, obtuse refers to the classification based on its angles, and isosceles based on its sides. Remember, isosceles, 2 equal sides, the third one is not. And then we saw that this middle one here was a right scalene. And this one was an acute equilateral. This one was an acute isosceles, acute scalene, obtuse isosceles. So the first name is the classification based on the angle, and the second name is based on the classification on its sides. Okay, good. Good, good, good. And then what we did was we talked about that triangle sum theorem. And we saw that there's many, many, many ways to prove the triangle sum theorem. Here are a few videos. I did one in class yesterday using parallel lines cut by transversals. If you need review of that, please let me know. And right above this video, go ahead, just look, send your eyes up. Right above this video is another proof that doesn't use mathematics whatsoever. In other words, no computation, but uses nothing but scissors and paper and cardboard that you're welcome to watch that I put together as well. So again, there's another proof of the triangle sum theorem. In other words, all 3 angles of any triangle add together to make 180 degrees. If you'd like to know more proofs, do let me know. Believe me, for thousands of years, there have been many, many proofs, okay? But the 2 that I showed you, the video, just the one above, and the one in class yesterday, maybe that's enough evidence for you. If not, do let me know. I'd be happy to show you more. Well, let's keep going with this, right? Because today I want to talk about when can a triangle not exist? We've all been talking about triangles that can exist. Well, are there parameters in which they cannot exist? Well, absolutely. Here we have 9 different combinations of the words acute, right, and obtuse, and equilateral, scalene, and isosceles. Let's find out which ones can exist. Can you have an acute isosceles triangle? Think about it for a moment. And the answer is, yeah, you can. There's one right there. You can have an acute isosceles triangle, no problem. What about a right isosceles triangle? Think about it. What do you think? 90-degree angle, 2 sides equal. Yeah, why not? There's one right there. Right isosceles triangle, right? These 2 sides are equal, and there's your right angle right there. What about an obtuse isosceles? That one's a little bit more tricky. Can you have an obtuse isosceles? Of course you can. Of course you can. Two angles right there equal. There's your obtuse angle. And the acute one, those two sides right there were equal. Okay, so you can have an acute isosceles, right isosceles, obtuse isosceles. So isosceles triangles, you're a go for all the different types. What about scalene? Scalene in the same boat? Can you have an acute, right, and obtuse scalene triangle? Acute scalene, think about that for a moment. Acute scalene, all three sides not equal in length. Yeah, absolutely, there you go. There's your acute scalene. All three sides not equal in length, and all three angles acute. What about a right scalene? All three sides not equal, a right angle. Yeah, there's one right there. Right there's your right angle right there. And look at all three sides, not the same length. Obtuse scalene? Totally. There it is right there. All three sides not the same length. And there's your obtuse angle. You can see it right there. Okay, so if scalene is a go for acute, right, and obtuse. Nice job, scalene and isosceles for the win. Equilateral. Are you a fickle beast? Acute equilateral. Can you have an acute equilateral? Yeah. You absolutely can. In fact, they're all acute equilateral, aren't they? All three sides, the same length, all three angles, the same angle measure. Right equilateral. Think about that one for a moment. Right equilateral. Possible? Impossible? If you said impossible, you're right. You can't have a... No pun intended. You are correct. You are correct. You cannot have a right equilateral triangle. That doesn't exist. Because all three angles of an equilateral triangle have to be 60, don't they? Can you have an obtuse equilateral triangle? Well, based on what we just said, no, of course not. You can't have an obtuse equilateral. So equilateral triangles, very specific. You can only have an acute equilateral triangle. A right or obtuse equilateral triangle doesn't exist. If you think it does still, if you're not convinced, go ahead and try to construct one using GeoGebra or pencil and paper and a ruler. Go right ahead. I challenge you. Go right ahead. But all the others, yeah, they're a go. Isosceles, you're good. Scalene, you're good. Equilateral, you're a little bit picky when it comes to your angles, aren't you? Well, there you go, folks. But we're not done. We're not done. No. What about based on the angle measures alone? Can these triangles here that I constructed, can they actually exist? Did I just kind of create triangles that are impossible? Like, look at this top one here. Well, we know based on the triangle sum theorem, all three angles have to equal 180 degrees. So did I just create something that cannot be created? In other words, did I label it wrong? Think of it that way. Let's see here. 20 degrees plus 150 degrees plus 25 degrees. Well, let's see here. If I add 20 plus 150 plus 25, I get 195 degrees. So while this triangle that I created, you can see it, I pretty much mislabeled it, right? This triangle cannot really exist in the real world if you were to actually take a pencil, paper, ruler, or popsicle sticks, or straws, or anything that would resemble side length and actually try to create this in real life. You couldn't do it. Think of it this way, I mislabeled this triangle. You can't have a triangle with all three angles equal to 195 degrees. That's impossible. Same with this tall drink of water right here to its right. Let's see here. We got a 15-degree angle up there and two 75-degree angles down there. Looks to be an isosceles triangle here, but let's confirm that it actually is a triangle. 15 plus 75 plus a third and final 75 here. Doing my calculations here, and I get 165. So, well, too low this time, right? 195 degrees, too high. 165 degrees, too low. So again, this triangle is actually very, very much mislabeled. This triangle couldn't exist in real life. Again, think of it this way. I mislabeled this triangle's angle measures. Can't exist in real life. Again, I challenge you. Take some straws, popsicles, pipe cleaners, you know, those fuzzy wires that we all used to play with. Pipe cleaners, you guys know the thing. Try to create this triangle. It can't happen. Can't happen in the real world. All right, so we saw that based on the angle measures alone, it's pretty easy to determine if a triangle can or cannot exist. You simply add them up. If they do equal 180 degrees exactly, okay, they exist. If they don't equal 180 exactly, well, then they don't. Whether that's too high or too low, doesn't matter. It has to be exactly 180 degrees. Exactly 180 degrees. You know what? We've talked about the angles of a triangle enough. Let's get back into talking about the sides of a triangle. And to do that, I present to you, ladies and gentlemen, the GeoGebra Triangle Challenge. That's right, I offer to you the GeoGebra Triangle Challenge. Now, let me explain this challenge. And if you do it correct, here's what you win. And this is not just the first person who does it correct. This is every person that does it correct. You're going to go into GeoGebra by clicking the link right here. And using GeoGebra, and I'll show you how in just a moment, you're going to create 6 triangles. And here are the requirements for all 6. Triangle 1 has to have side lengths of 3, 5, and 7. Triangle 2, 5, 7, and 10. Triangle 3, 7, 9, and 15. 4, 5, and 6. You can see the side lengths there. I'm going to show you how you can create side lengths exactly using GeoGebra. Okay, so you don't have to kind of like drag the line segment around a bit to get it exactly. No, I'm going to show you how you can do it exactly very, very easily in just a moment. Okay, so what you're going to do is on the same GeoGebra screen, create all 6 triangles. Once you have all 6 triangles created, take a nice screenshot of all 6 triangles in one screenshot, email it to Mr. Ripes. Again, folks, it's not the first person who does this correct. It's anyone who does this correct. You'll win the prize. And what is the prize? Oh, ladies and gentlemen, the prize is the following. Listen carefully. If you do this GeoGebra challenge correct, and you email me all 6 triangles, and they're all accurate, you won't have to do any Alex Pats for the rest of the year. That's right. On Fridays, when we do our at minimum hour-long Alex Path, you're exempt for every single one for the rest of the year. Oh, this is correct. This is a good challenge. Heck, let me help you with the first triangle. Yeah, here, I'm going to help you do the first triangle. Check this out, folks. So I've gone ahead and clicked that link in OneNote and brought me right to this beautiful screen right here. All right, so what you want to do is you make sure that you have all the tools available to you because you're going to need all of them. So you'll have to click More. And once you do, all of these other tools will be available to you. And specifically, we're going to be using a ton. This one right here, segment with a given length. And it is you who are to give the length, okay? So let me show you. You know, I need a reminder. The first triangle has side lengths of 3, 5, and 7. Okay, we got this. Side lengths of 3, 5, and 7. So first, let's just create line segments 3, 5, and 7. So I'm going to click segment with a given length. I need to click a point, and then I need to type in how long I want it. I want it to be 3 units long, 3 inches or whatever, just 3. Okay, and there it is. Now the nice thing is, look at this. No matter what, you can't make it any longer. You click on these points, and you know how sometimes with a line segment, as we saw with our creating the monsters, you can make it longer or shorter, but because you said this has to be 3, it's not getting any longer. But you can still move it around by clicking on the points, and you can still rotate it around by clicking on the points. And you're going to need to do that to put together this triangle, okay? So, but no matter what, it's never going to get longer than 3 units. So nice. All right, what was the other one? I forgot. Oh yeah, 3, 5, and 7. All right, so let's make 5. Oops, let's make 5 now. Okay, segment with a given length. I need it to be 5 units long. There it is. There's my 5 units long. All right, now I need another one that's 7 units long. So I'll click down to get my point, and boom, there they are. All right, so let's see. Let's make sure that these are labeled. Let's show the value. Oh, there's my 3. Okay, this one you might recall with the 5, so let's show the value so I don't forget that. And let's show the value of this one. And that one's 7. All right, cool. So I got my 3, 5, and 7. I got to put these together. I got to make a triangle. Okay, so let's see here. You know what? That doesn't matter which side is constructed and put together first. No, none at all. So let's see here. Let's put this L sub 1 and M sub 1 together. Okay, good. Now I need to take this third side right here, the 7 long. I gotta, let's see here. Okay, well, can I connect it there? Yeah, there you go. Make that nice connected right there. Okay, good. Now I gotta take this K sub 1 and this O sub 1, this K and this O sub 1. I gotta bring those together. So can I do that? Whoops, I need to flip this around so that I can do it. Let's see here, can I get it? Let's see here. Ooh, I'm getting close, Okay, let's see, can I move this? Oops, I gotta flip this one around so that K is connected to M, so I can manipulate all of that. Oh, I'm so close. Okay, move this one out, move this one up. Oh, so close. Almost there. Okay, get out of the way, Pete. There we go. I think I have done it. And boom! Look at that. A triangle that has side lengths of 3, 5, and 7. I'm good. So I was able to create this first triangle, no problem. Can you, ladies and gentlemen, create the other 5? Okay, so 1 is done for you. You still have to do 1, okay? I showed you that it can be done. Can you create 2, 3, 4, 5, and 6? Okay, so you're going to pause the video now, and you're going to work on this. And when you've got all 6 triangles, when you think you have all 6 triangles constructed on one GeoGebra screen, take a screenshot of that, email it to Mr. Ripes. Again, not the first person, but every student that is able to accomplish this challenge. You won't have to do the ALEKS assignments for the rest of the year. The ALEKS Path assignments, that is, the ones on Friday. Okay, the normal ALEKS assignments you still have to do. But the Friday ones that last at least an hour, nope, you're good. Rest of the year, don't worry about it. So pause the video now, try it. When you feel you're done, or you feel you've given up, unpause the video, and we'll see what the results are. So, ladies and gentlemen, ideally you have emailed me, Mr. Ripes, your 6 triangles, or you've given up. I do have to apologize. Because you probably spent a good number of minutes putting these triangles together, but yeah, I just sent you on a complete fool's errand. I really did. Because the first 3 triangles, no problem. You can create those without a doubt. But the final 3, triangles 4, 5, and 6, oh, I'm sorry, those are impossible triangles to create. You could not construct those. You couldn't. Triangle with side lengths 1, 8, and 10? Nah, impossible. 2, 2, and 6? Nah, impossible. 3, 5, and 11? And maybe you got something that looks like this for each of your 6 triangles, or at least the first 3 triangles. And maybe something for the impossible triangles 4, 5, and 6. You got something that looks like this. So again, if you spent a good number of moments and now you're frustrated, you want to punch a wall, you want to punch Mr. Ripes, yeah, I completely understand that. You know, I completely understand that. Now, granted, we are also right now in quarantine and isolated from each other and learning off campus, so punching Mr. Ripes is not really an option. And maybe it'll be next year as your 8th graders when we're all back together again. I'll consider it. Anyways, moving on. Why? That's the question. Why are triangles 4, 5, and 6 completely impossible? It's because of something called the triangle inequality theorem, which helps us to determine if a triangle can or cannot exist. And it's a very beautiful theorem. It uses inequalities, hence the name triangle inequality theorem. All right, so what is it? Well, the triangle inequality theorem is this. The sum of the lengths of any 2 sides of a triangle is greater than the length of the third side. What the heck does that mean? Let me explain, folks. Notice how there's inequalities here? The triangle inequality theorem simply states that you can take any 2 sides of a triangle, because you know there's 3 sides to a triangle, so take any 2 sides, I repeat, any 2 sides, add them together. If you take any 2 sides of a triangle and add them together, that sum has to be, I repeat, has to be, one more time, has to be, that sum has to be greater than the third side that you didn't add together. In other words, if you took A and B and added that together, that has to be greater than C, as we see right there. Or, you could take A and C, add those together. Has to be greater than B, as we can see right there. Or, you can take B and C, add those together. Has to be greater than A, as we can see right here. Now here's the thing about the triangle inequality theorem. All three inequalities have to be true. It's A plus B has to be greater than C, and A plus C has to be greater than B, and B plus C has to be greater than A. It's not one of them has to be true. Oh, no, 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 no. All three have to be true. If one of them is not true, that triangle can't exist. If only one of those inequalities is not true, the whole triangle cannot exist. And again, it's a very strong and, okay? All three have to be true. And another thing, folks, notice these inequality signs. Greater than symbols. Not greater than or equal to symbols. No, 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 no. The sum of the two sides of a triangle cannot be equal to the third side. It has to be strictly and exclusively larger, greater than. So now let's apply this to our 6 triangles above and see if it fits, if they can or cannot exist. Well, triangle 1 did exist because apparently it is going to work in the triangle inequality theorem. All right, so let's see here. It doesn't matter which sides we start with. Heck, let's start with 3 and 5. If I add together sides 3 and 5, let's see, 3 plus 5. Is that greater than the third side 7? Yeah, 3 plus 5 is in fact greater than 7. Okay, but it's not enough to just check 2 of the sides if it's greater than the third. You got to check all the sides. You got to make all the combinations here. So now let's take 3 and 7. 3 plus 7, is that greater than the third side 5? Of course it is, you know that. Okay, now which combination have I not yet made? I've added 3 and 5, which of course is the same as 5 and 3, right? If you do 3 and 5, you are also satisfying 5 and 3. This we know. If you do 3 plus 7, that's the same thing as 7 plus 3, so you don't have to double up your efforts. Oh, I didn't put together 5 and 7. Okay, so 5 plus 7. If I had 5 plus 7, is that great? Oh, yeah, 5 plus 7 is greater than 3. Notice that all 3 inequalities are true. So therefore, this triangle can exist. A triangle with 3, 5, and 7 side lengths does exist, as we proved in GeoGebra and as we proved using the triangle inequality theorem. Triangle 2. 5, 7, and 10. Let's see here. Let's make all the combinations. And again, it doesn't matter which order you put these together. Let's see. 5 plus 7. Yeah, that's greater than 10, right? 12 is greater than 10. All right, okay. 5 and 10. Let's put those together. 5 plus 10 is greater than the third side 7. Yes, 15 is greater than 7. Okay, good. Now, I haven't put together the 10 and the 7. So 10 plus 7. Yeah, I do believe that to be greater than 5. All 3 inequalities are true. So therefore, triangle 2 does exist, as we can see here. Triangle 3. That one works. 7 plus 9 greater than 15. Sure, because that's 16, right? 7 plus 15 is very much greater than 9, and 9 plus 15 is very, very much greater than 7. So the first 3 triangles, all 3 of them did satisfy beautifully the triangle inequality theorem and thus can exist. Let's see what happens when the triangle inequality is not satisfied. All right, so triangle 4 is our first failure of a triangle. You're not a triangle. You're not a triangle. It's having an identity crisis. It's looking at the mirror saying, I'm a triangle, I'm a triangle. But in reality, it's not a triangle. Sorry, triangle 4 with side lengths 1, 8, and 10. You do not satisfy the triangle inequality theorem. Let's check all 3 inequalities. Okay, so let's see here. 1 plus 8 is greater than 10. Okay, I'm not sure about that. But you know what, just for completionists' sake, let's put together all the other inequalities as well. 1 plus 10 is greater than 8. Oh, okay. 10 plus 1 is greater than, whoops, I already did 10 plus 1, sorry, there's the one I just did. 1 plus 8, 1 plus 10, and 8 plus 10 is greater than 1. Okay, well, you know what? Some of these are true, right? 8 plus 10, that's greater than 1. That one's good. 1 plus 10, yeah, 11's greater than 8. Oh, boy. It's that first one that fails. 1 plus 8 is not greater than 10. You see, when one inequality fails, the whole thing fails. You can't have a triangle that exists like that. If one inequality fails, So in other words, you really didn't need the other two inequalities, because in order for a triangle to exist, all three inequalities have to prove true. And if one of them doesn't, you know that triangle can't exist. You don't really even need the other two inequalities because, well, one of them failed. So the other two are completely a moot point. All right, good. So we just proved that triangle 4 doesn't work. Let's see something similar with triangle 5. Let's see here. 2 plus 2 is greater than 6. Don't think so. I don't think so. I think that's our failure one, isn't it? Yeah, so therefore it doesn't exist. But, just for completion's sake, let's do the others. Let's see. 2 plus 6 is greater than the third side 2. Wow. Okay, so that one does work, and if we do 2 plus 6, of course, 6 plus 2 is greater than 2, because that's the third side also being another 2. So 2 and 6, 6 and 2, yeah, those worked. Okay, those worked, but clearly that first one did not. So therefore, nope, doesn't work. And the sixth and final failure, epic failure of a triangle. Here are our three inequalities. Let's start at the bottom. 11 plus 5 is greater than 3. Well, yeah, because 11 alone is greater than 3. 3 plus 11 is greater than 5? Yes, of course. 3 plus 5 is greater than 11. Oh, survey says. You guys know that sound of Family Feud. Yeah, so that didn't work. Okay, so now we see that all 6 triangles, some do, the top 3, satisfy the triangle inequality theorem, and the bottom 3 do not. So once again, folks, I apologize. Everyone failed the challenge. And I know you were kind of destined to fail anyways. So I apologize for that. But hey, you learned about the triangle inequality theorem in the process. Yes, the triangle inequality theorem tells you when, based on the sides, a triangle can or cannot exist. All right, let's finish this up. Here are 2 triangles here. Can they actually exist? Or are they mislabeled? Tell me if they can or cannot exist. Pause the video now, try it on your own. Unpause it when you're done. Let's see what you get. The first triangle, the one with 3.5 and 4.5 in one side lengths, no, that one can't exist. Cannot exist. But the bottom one can. All right, let's examine why the top one can't. It's because of that inequality sign. Remember, it's very specific. It is in a greater than sign. It's not greater than or equal to. It is exclusively greater than. So while 3.5 plus 4.5 is in fact greater than 1, and 1 plus 4.5 is in fact greater than 3.5, here's where it fails, this top one. 1 plus 3.5 is not greater than 4.5. It is equal to 4.5. And because that's greater than, not greater than or equal to, this is a false statement. In other words, 4.5 greater than 4.5, that's not true at all, okay? Those two numbers are equal, not greater than each other. So therefore it can't exist. But the bottom triangle, sure. 7 plus 9.8 is greater than 13. 7 plus 13 is greater than 9.8, and 9.8 plus 13 is greater than 7. So that one did exist. It can exist. This one up here, while you can look at it, it's just simply mislabeled, okay? One of those sides, or maybe 2 of them, who knows, or maybe all 3, are just simply incorrect. Ladies and gentlemen, using this triangle inequality theorem, you should be able to work on today's ALEKS assignments. I'm going to have a Zoom classroom open today. You are welcome to pop it in out with whatever questions you have based on anything we've been talking about throughout this week, including this topic of the triangle inequality theorem. It is YouTube, so I do have to end the video by saying be sure to like, comment, and subscribe. Click that bell for notifications. Hope to see you guys in the Zoom classroom.